Hello, I'm Rob Bies, and I'm faculty at the University at Buffalo. And I will be presenting part 2 of a vignette on population pharmacokinetic modeling. So in part 1 of this vignette, we covered elements related to the research question, the nature of an experiment, the data that were generated, and then mainly the visualization of the data. In part 2, we're going to now move into the actual model building. What are the elements of model contexts to explore? What models might we want to consider? What do we look at in terms of output? And what are some very basic elements of model evaluation? And how does that allow us to generate inferences about the pharmacokinetic characteristics of the drug? Again, we're going to revisit our quetiapine example from the NIMH-funded CATIE studies. So our general outline will focus on model building approaches, and this encompasses the criteria for model discernment, things such as objective function value or OFV, information criteria, graphical indicators. Then we consider what a structural base model search looks like. How do we approach generating initial estimates? What is an appropriate scope of potential models to explore? For example, 1 or 2 or 3 compartment models, linear, nonlinear, the target-mediated drug disposition-based elimination. How should we think about the between-subject variability that arises that is critical in a population pharmacokinetic analysis? We won't cover in detail any evaluation of the residual error structure in this part, but one would evaluate any systematic patterns in those residuals that would help guide model selection. We're also going to assess the impact of uncertainty in parameter estimates. And one may also evaluate mixture distribution for parameters, but mixture distributions are a little more advanced, and they are outside the scope of this vignette. We will then touch on basics of covariate modeling. So once you establish this base model, you search for correlation between normalized distributions of the individual parameters, we call those the etas, and individual specific characteristics. One could consider continuous versus categorical variables and structures that describe those relationships. And then what are the criteria for inclusion or exclusion? For the purposes of this part 2 vignette, we will cover the basics of a stepwise covariate modeling strategy. So let's start with the criteria for model discernment, the objective function. So many statistical analyses will return a numerical index of model fitness. This is often referred to as an objective function value. And if you're doing a nonlinear mixed effects modeling population pharmacokinetic analysis, for example, if you're using non-MEM, that objective function value is based on the likelihood. Actually, the value returned by non-MEM is -2 times the log likelihood. And why -2 times the log likelihood? Well, if you're comparing models, the difference in -2 log likelihood values is approximately chi-square distributed. So what does that mean? If you have a population pharmacokinetic model, you can compare models, if they're nested, with different degrees of freedom. You typically make one change at a time. And you can evaluate whether or not that change appears to have improved the model description of the data statistically by looking at the change in that -2 log likelihood value. For example, if your objective function value changes by 3.84 points, because it's -2 log likelihood, if it's 3.84 points lower with one change in the model, i.e. one additional parameter, then that means that you have a significant effect at the p=0.05 level. If the objective function value change is 6.61 points with one change in the model, so one additional parameter, then it's significant at the 0.01 level. So it gives us some guidance. It's not the only thing that should be considered. There are many elements that one must take into consideration when building models. Another criteria for model discernment are the information criteria. I have two examples here. The AKA key information criteria, which many people may be familiar with. This is a function of that -2 log likelihood, or that objective function value, but there's a penalty added to this. And that penalty is 2 times the number of parameters that are in the models. So if you have a more complicated model, if you add parameters, your information criteria value will not be as low or as optimal. Similarly, the Bayesian information criteria, sometimes called the Schwartz-Bayesian criteria, is a function of the -2 log likelihood plus a penalty that comprises the product of the number of parameters multiplied by the natural log of the number of data points. So here you have a combination of number of parameters and number of data points. These information criteria do not give a strict basis for statistical inference based on statistical significance. What they do provide is whether the complexity of the model is supported by the observed data. So it's a binary decision. What is better or worse, but not a specific continuous value that tells you something has met a particular threshold with respect to statistical significance. So continuing along with criteria for model discernment, some other basic graphical indicators of fitness include various goodness of fit plots, such as the dependent variable versus the population predicted value. The dependent variable in this case is the concentration measurement versus the individual model predicted value. So it's adjusted for the individual observations and individual covariates. And then plots by individual that show the time course of the data, show the time course predicted by the model at the population level, and show the time course of the predictions from the model at the individual level. And then, of course, residual plots. But as I mentioned in the introduction, I won't be covering residual plots in this vignette. There are also visual and numerical predictive checks. And again, those will not be covered in this particular vignette. So let's go back to the basic goodness of fit plots for model discernment. The dependent variable versus pred plot. So again, the DV, dependent variable, are our observations. Pred denotes our population predictions. So those are predictions based on the dose, time, and adjusted for covariate values if those are in the model. Okay, and these are based on the fixed effects that are estimated in the pharmacokinetic model, the PK parameters, and the estimated covariate effects. So this is also sometimes referred to as the thetas. All right. Although thetas are not always strictly associated with fixed effects, they are typically so. So to aid visualization of producing this type of plot, you want to use the same range on the X and Y axis. Okay, so here we have the observed concentration and the population predicted concentration. So population predicted concentration on the X axis and the observed concentration on the Y axis. The dots are the values for each of the pairs of observations with predictions. This black solid line is the unity line. And this dashed line is a smooth through the data to see whether or not there appears to be a major departure from that line of unity. It's useful for diagnosing structural model misspecification And what you're really looking for is whether or not there's an even scatter of points on both sides of the line. The distances are less of a concern here because those are often adjusted for with other factors when considered the individual predictions. Okay. And again, regression line or a smooth gives you, should hopefully follow that line of identity. So considering this dependent variable versus population predicted, here's an example that shows a good model on the left, and this is from the ISOP model evaluation white paper, Montre et al., that was published in CPT-PSP. Here again, on the x-axis are the population predictions, and on the y-axis are the observations. And you see in the left panel that we match this line of unity quite well. We have an even scatter. On the right-hand panel, you see a misspecified structure, and you see some departure in that smooth from the line of unity. So something systematically not being adequately predicted, or alternatively predicted with some degree of bias. Another basic goodness of fit plot is the dependent variable versus individual predicted plot. Again, the dependent variable are the observations. The IPRED are the individual predictions. So the predictions based on the independent variables, fixed effects, thetas, and the adjustment for the between subject random effects, i.e. etas and omegas. So conditional on a patient's data and the population model, the model can make an adjustment to try to predict these values more closely, and these points should be closer to the unity line as a result. Again, to aid visualization, we want to use the same range on the X and Y axes. We want to include a line of identity, right? That would be the perfect fit. That's this black line on the plot on the right here. And you want to include a locally weighted regression line. You can see that follows, for the most part, it follows the identity line. And that's what we really are looking for. Specifically, again, on the plot, you have the observed concentrations on the y-axis and the individual predicted concentrations on the x-axis. So here we have an example of the IPRED versus dependent variable plot for the true model, and the IPRED versus dependent variable plot for a misspecified model. And again, this comes from the ISOP model evaluation paper, Montre et al., CPT-PSP. And you see that on the left with the true model, we have a line of identity. The locally weighted regression line follows that closely. The points are very tightly distributed around that line of identity for the true model. In the right-hand panel with misspecified structural model, you can see that the points are systematically shifting around that line of identity, and that the locally weighted regression also departs from that line of identity. So it suggests that you need to rethink your model structure, because there is some sort of a misspecification in this model. And even with the adjustments, that fundamental structural model is unable to describe the pattern of the data vis-a-vis the concentration versus time profile. The next basic plot to evaluate fitness is this population predicted and individual predicted and dependent variable versus time by patient or by ID, by individual. And this is a simple way to visualize how well the model describes individual profiles. And it's useful for identifying observations that warrant double checking for potential mistakes. It could be, extreme values and that sort of thing. So what does this plot look like? Well, here we have a matrix of individuals. So each of these panels represents a different individual. We have concentration on the y-axis. We have time on the x-axis. And the dots are the actual observed data, the observed concentrations in this case. And we have two different lines. We have a blue line and a red line. The blue line is the population predicted value. And if we don't have covariates in the model, and all the patients got the same dose, this blue line is going to be the same for all individuals, okay? Because it is using the population pharmacokinetic parameters. The red line is the individual predicted line. So these are adjusted for the observations. So where we can see this most dramatically is an individual 2004. You see that they have this one high concentration. So the population prediction is this blue line, and it shows the same as every other blue line in all these panels. But because this solution is conditioned on on individual 2004's data for this particular panel, the individual prediction is actually closer. You can see that it's matching those points a little closer. At least it's trying to match that higher initial value. This allows you to evaluate whether you think there are outliers, whether individuals seem to be grouped into different kind of subpopulations in terms of their concentration time profiles, and to evaluate whether or not at the population level, beyond the DV versus PRED plot, the predictions seem to be reflecting the data with respect to evenly under and over predicting these observed data. So the next component we're going to talk about are the initial estimates. And these are basic principles with respect to initial estimates. And some of this was taken from a paper in TCP, and I have the citation on subsequent slides. So all nonlinear regressions require initial estimates as a starting point for the search of a likelihood or search for an objective function. And so this, it doesn't matter what software you're using, you need to provide initial estimates. So there's some strategies for considering the calculation or determining those initial estimates. You could do a non-compartmental analysis on the data that you have. For example, a smooth we showed for quetiapine. Maybe there's other literature. Maybe this is a drug that has already come out, and there maybe in different populations there are population pharmacokinetic parameters or even general pharmacokinetic parameters published. The FDA website, in particular, the redacted ND reviews, or clinical pharmacology review in particular, are available as a result of the Freedom of Information Act. And these often provide average profiles from phase 1 and 2 studies with PK characteristics. Alternatively, the drug label in the clinical pharmacology section often has an indication of the general pharmacokinetic characteristics. And those are all places that you can go to evaluate this. Now, if this is a brand new drug and you've got your, then you will have to use the data that are available to you from the study. Key challenges include sparse sampling. So, you could do time after dose and consolidate by dosages, similar to the plot that was shown in part 1 for quetiapine. We could have multiple points, create a smooth, and do a non-compartmental analysis on that smooth curve, at least give us some sense of what reasonable clearance and volume of distribution parameters might be. So this is often a non-trivial issue, as poorly chosen estimates can increase the runtime for any nonlinear regression problem or any nonlinear mixed effects problem. And in particular, if you're using non-mem and you're using some of the gradient methods, and the first order conditional with interaction and the Laplacian, it takes longer for a solution to be discovered. And it can also result in poor or incorrect final parameter estimates. Some of these gradient-based methods are quite susceptible to local minima, and if you don't have good initial estimates, you may end up with a solution that you think is a stable solution, but it actually represents a local minimum in terms of the estimated pharmacokinetic parameters. So what parameters require initial estimates? Well, our fixed effects values, typically thetas, right, are typical values. So these are values in the non-mem control stream. And you also probably want to provide some bounds. So for example, if you're estimating a clearance value, clearance is a physiologic process, has to have a positive value. It's probably not 0. So you want to put some bounds in, and it's probably not 300 million liters per hour. So you may want to give not only an initial estimate, but some ranges. One also must provide initial estimates for the random effects value. So for the between subject variability and between occasion variability that you might pose in a population pharmacokinetic model, these initial estimates are provided in the dollar omega block, and it provides the initial search for a value representing how variable that parameter is between individuals or between occasions, depending on which one it is, BSV or BOV, in the population. And then the residual unexplained variability. And for the residual unexplained variability, you may want to start with values that are close to the assay variability, the limit of quantitation and the CV of that particular assay. So speaking a little more specifically about fixed effects, theta, or typical values, or population averages, this is strictly the central tendency, so the population typical values. You're not providing any information on the variability or dispersion or uncertainty across the population. And again, we're using a best guess. And we talked about strategies for that best guess. Again, literature is a good source of information. The authors from the TCP paper suggested some general ranges for linear processes or typical first-order processes in pharmacokinetics for clearance and volume and absorption processes, but it really will depend on your specific drug. Keep in mind that the values might be higher for the extravascular dose given the divisor of F. These are really, if it is an extravascular dose, it's clearance over F and volume over F, etc. So what about for our example of quetiapine? Well, there were multiple values available from the literature, and that this table shows the parameter values. So these were typically for one compartment models. And there were 3 publications in the peer-reviewed literature, which was actually in a toxicology context with overdose, Kimco, which was an early evaluation that used the phase 1 and early phase 2 studies to generate the model, and Zhao, which was from actually the company that developed quetiapine with a larger data set. We even had some values from the Katie studies. So these appeared in a chapter reflecting this of a book that was published from the studies, but were incomplete. You see, there's no residual error provided, and there was other limited information. So we have quite a rich set of information to start with, and we can use those as initial estimates and also give us a sense of what sort of model structures we may want to explore. So what is the scope of a structural model search? Well, we might consider the number of compartments. So this could be 1 or 2 or 3 compartments, linear mammillary models with first-order processes, perhaps. The type of an absorption model. Is this a first-order absorption? Is this a zero-order absorption? Is this an Erlang distribution with a catenary chain in terms of the delay in absorption? Is there a lag in the absorption? In terms of elimination pathways, does this appear to be a linear elimination or a nonlinear elimination? There may be other contributors to the drug disposition, to the pharmacokinetic profile. Is this a drug that is subject to target-mediated drug disposition? What are the protein binding characteristics? Are there transporters that act on this drug? So let's go back to the profile that we observed for the quetiapine study. So here again, we have a dose normalized concentration on the y-axis and the time since last dose on the x-axis. And if we look at this, remember that these appear to be linear processes. These are multiple doses, and there are not doses clustering above or below from part 1 of the vignette. And the general input and offset look close to sort of straight lines. There's not a lot of indication of a nonlinear process here, so we probably will explore only linear processes and maybe 1 and 2 compartment models. So we thought about, okay, that's the scope maybe for our basic structural model. What about the between subject variability strategy? So we have parameters in this pharmacokinetic model, and they may vary at random between individuals, right? This is our between subject variability. And there are generally 2 schools of thought on the approach to this. One is to put a between subject variability term on every fixed effects parameter. So there's between subject variability on absorption, there's a between subject variability on the volume of distribution, and there's a between subject variability on the clearance. The other school of thought is to put no between subject variability and start with what is effectively a naive pooled analysis or a naive pooled minimization. And if you go back to the original lecture, we discussed naive pooled analyses as one potential strategy and also highlight some of the limitations there. In terms of the structural and base model strategy, if we add the between subject variability to all fixed effects simultaneously, we may be able to observe where the BSV estimate is very, very small. We can decide maybe we should remove it. Maybe, a 0.5% between individuals is not really going to have any impact. Now, this might also be very small because the data are so variable or they're multimodal, and the penalty for having an enormous between subject variability estimate is greater than the penalty for not predicting those concentrations as well, which is the balance that's calculated in the likelihood for these nonlinear mixed effects population pharmacokinetic models. Similarly, if the BSV is estimated but it's extremely large, maybe it's not a single distribution. Maybe there are multiple modes. For example, if you have a drug that is eliminated by cytochrome P450 2D6, we know there are poor metabolizers that have almost no metabolic activity. We know there are intermediate and extensive metabolizers, which have a typical elimination characteristic that are noted for those drugs. And we also have individuals who are ultra rapid metabolizers and will have extremely low levels after concentrations. Those do not arise from the same distribution. They're centered in different positions in terms of the relative clearance. Now, there are also considerations of off-diagonal elements. What are the expected correlations amongst parameters? And we should explore those block structures. Exploration of off-diagonal elements will be beyond the scope of the vignette today. So the other strategy is to not put between subject variability on in the initial analysis, basically do a naive pooled assessment, and then add BSV parameters one at a time, and then decide whether it should be kept in the model. Do we use the statistical criteria? Do we need to have between subject variability on multiple parameters? Perhaps there's a dependence that we might miss if we do this. Again, we need to consider non-normal distributions and multimodal distributions and off-diagonal elements. So there are various also residuals that we want to consider, and you can evaluate graphically using residual patterns. And I'm going to touch on this in a very superficial way. We have the RES residual, which is the population residual, the WRES, which is the weighted population residual. This is only really appropriate for the first order estimation method. The conditional weighted residual, which is appropriate for the first order conditional estimation. The conditional weighted residual with interaction, which is appropriate for the first order conditional estimation with interaction option. The individual residual, which is the newer versions of NOMM is now being automatically calculated. In the older versions, one had to incorporate this into the error block. And the individual weighted residual, and the weighting depends on the error structure that you select. Helpful visualizations include the population residual versus dependent variable. This will tell you right away if you cannot use an additive model. You'll see a fan structure with increasing distance from that unit from the zero line with increasing dependent variable. The conditional weighted residual versus dependent variable, conditional weighted residuals versus time, individual weighted residuals versus dependent variable, and the individual weighted residuals versus the dependent variable. So let's look at some model output. So we talked about selecting model structures and having a scope of search. So this is from our analysis of the quetiapine data set from the Katie studies. On the left table, we have output from a one compartment model analysis, linear absorption, first order absorption, first order elimination. On the right panel is a two compartment model for the same data set. The numbers are the parameter values. You see the units are provided here. For the thetas, these are the fixed effects, okay? These are your typical values. The population value of clearance, 107 for the one compartment model, 112 for the two compartment model, for example. And we have volume absorption rate for the two compartment model, V2, V3, because it's an extravascular dose. And this is the coding in NOM, and then the intercompartmental clearance is Q. The omegas are the between subject variability on those parameters. So you can see that we have the omega clearance, right? This is the between subject variability on clearance. The value returned by NOM is 0.378. The actual, when we convert that to a percentage between subject variability, it's about 68%. So the values in brackets are the percentages between individuals, between individual variabilities. Again, these are the between individual variabilities, and in brackets, we see the actual percentages, and the numbers returned by NOM are presented as the main numbers here. These are basically like a CV, not exactly, depending on which estimation method you're using, you have to do a different back transformation. And then we have our residual unexplained variability. These are these sigma values. And at the very bottom, we have our OFV, the objective function value. And you can see for the one compartment model, this is the value of 10182.169. And you remember that the objective function value is -2 times the log likelihood. And the lower, the better for these values. If we compare this to the two compartment model, we see that this objective function value is 10,062.035. That's almost over 120 points lower. You remember, for 1 degree of freedom, right, a change of 3.84 points was sufficient to deem a statistically significant improvement. Now, here we have 2 degrees of freedom, because we are adding these extra volume of distribution, B3, and the intercompartmental clearance, or you could argue 4 degrees of freedom if you are including the extra between subject variabilities. But the 120 points on a chi-square, even for 4 degrees of freedom, is highly significant. So this would point us towards selecting a 2-compartment model structure. Now, this is in conjunction with evaluating graphical patterns, residuals, etc. Now we're considering between subject variability. You'll see that the estimate for the between subject variability on the peripheral volume of distribution here, omega V3, is extremely low, right? 0.4% between individual. Well, that means it's probably not having a significant impact on the disposition, and it's an extra parameter. So if we basically remove this parameter, fixing it to 0 in the right-hand side table here, we see that the objective function value actually got better. So the estimation was more stable. And the other parameters actually are all reasonable as well. And you'll see that this V3 value actually starts to get a little bit lower and closer to what was reported in the literature. Well, what about model uncertainty? We can also consider the parameters with respect to the model uncertainty. This is often also referred to as the relative standard error of the parameters. It's basically how well do we know those parameter values? We do an analysis and we determine, okay, well, can we rely on that parameter estimate? So you'll see that most of these values, and these are the values in brackets or parentheses next to the main numbers here in both of these tables. And what we see is that they're generally relatively low, with a couple of exceptions, but the major exceptions we left in. Now this is the between subject variability, or the omega V3. Again, we have a value of 2.3% in this case, but the uncertainty in this estimate is 211,000% plus, which suggests that value could assume just about any number, any value, and you would get a very similar solution. So these particular uncertainties or relative standard errors are calculated using something called the Fisher information matrix. What is the Fisher information matrix? If you're running most nonlinear mixed effects modeling software, a variance covariance matrix of the parameters is determined. That matrix is inverted, and it allows one to make an inference about how much worse the model fit gets if you change the parameter value. And that is the basis of the determination of these uncertainties in these parameter values in very rough terms. One can also obtain these values using a non-parametric bootstrapping approach, but that's outside the scope of this vignette. So essentially, if we remove, again, this between subject variability, we really get no change in the objective function, and the model stays about the same. And our estimates are all reasonable, so there's no reason to include this. So the uncertainty in this case on this parameter estimate pointed us in the direction of modifying the model, okay, by removing this element. So let's talk a little bit about basic covariate modeling. And the technique I'm going to touch upon in this part 2 vignette is stepwise covariate model building. And this involves steps called forward addition and backward elimination. So you start with our base model. We talked about building the base model and making those selections. And then you test the covariate to determine which one improves the model most significantly. So you test each covariate individually. You get a set of objective function value changes or differences, and you evaluate which ones are significant, and then rank order which one, the level of significance, how many points did this change by. And you can add this covariate to the model, starting with that most significant covariate. Then you add the second most. Did the model get better or not? If it didn't get better, then you remove that second covariate. You add the third one, you check, did it get better or not? Oh, it got better. So you leave that one in, for example, and you keep doing that until you have no further improvement. Then you have this full model with covariates, so then you start removing covariates, but in a different order. So you don't start with you don't remove the last covariate that you added. You remove a covariate, maybe the most significant covariate that was added during the forward addition, and you evaluate whether or not the model fitness got worse, i.e. that objective function value went up. And typically you have maybe set an alpha threshold for forward addition of 0.05, so that would be 3.84 points. And in the backward elimination phase, you change that threshold maybe to 0.01, so 6.61 points. You keep on doing this until no further worsening is observed, and you have your final model. So this is sort of the most basic technique. There are lots of other techniques, but again, they are outside the scope of this second vignette. What are the strengths of stepwise covariate modeling? Well, it allows selection of covariate relations from a large set of candidate relationships. It has a reasonable predictive performance. There's a lot of experience with this approach. There's an economy in which models to test, and avoids many problems associated with search based on empirical Bayes estimates, for example. It allows you to account for varying amounts of information between subjects, time-varying covariates, and a single framework for model selection. I think, oh, this is terrific, except there are some substantial weaknesses here. There's no guarantee that you'll find the best model. There's a selection bias. There's an increased risk of false selections for relations with lower power. And if your covariate, right, if the power to detect the covariate is less than 100%, then the coefficients are generally overestimated, i.e. the impact on the parameter value. And the confidence intervals are underestimated. You're doing all these different tests and you're getting different sort of differences in objective function value and crossing thresholds, but often multiple testing penalties are not applied. And we don't know what the appropriate penalty would be to apply in this case. It's not designed really for generating predictive models, and many runs may result in unsuccessful terminations or local minima. So stepwise covariate modeling is shown in this figure here, starting with a base model, looking at diagnostic information, test all the suspected covariates by adding them to the base model independently, one at a time. Pick the model with the most significant covariate, add the covariate to the base model. Okay, then you repeat, come back and say, take the second most significant and add it. Did the model get even better? If it didn't, remove. If it did, keep this and keep cycling until you have your forward addition model there at the bottom of the first column of boxes here. And then our backward elimination, you test the effect of removing all covariates independently, one at a time. Maybe start with the most significant covariate from the model. Just don't do the exact same order that you, or reverse of the same order that you did in the forward direction. And you end up eventually with a new covariate-based model, and you keep repeating this removal until you get no further worsening in the model, and then you have your final model. So to summarize our model building vignette, we have multiple considerations. We have to come up with rules for discerning what we think a good model is. We have numeric indices to help guide this, things like objective function value, information criteria, parameter uncertainty. There are graphical indicators such as residuals and these various plots we discussed. We have to come up with initial estimates. We can go to the literature or do a non-compartmental analysis of average profile over the population from data that have been generated. We decide on a scope of the model search. What is an appropriate space to search in terms of number of compartments and different processes, linear, nonlinear elimination, absorption processes. How do we handle the stochastic elements of the model, the between subject variability? Do we put this on every parameter to start with, or do you one at a time? The residual unexplained variability. What is an appropriate model there? Is it additive? Is it proportional? Is it a combination of the two? And then we start to consider covariates. How do we incorporate these? How do we look at potential relationships? And what does that mean? Are we in danger of missing certain dependencies amongst covariates? And as we saw from the part 1 exploratory data analysis vignette, one has to be very careful about covariates that are correlated amongst different arms or even within different characteristics. Because what is the characteristic that is driving the relationship with the response? And if you have correlation, that's very, very difficult to tease apart. So there were some elements that were not covered in this part 2 vignette. That is a more specific evaluation and graphical evaluation of residuals, bootstrapping techniques, visual predictive checks, numerical predictive checks, and numerical predictive distribution errors. And that would be the subject of future vignettes. Again, I would like to acknowledge Kristen Vigos at Johns Hopkins University, a faculty member there in the Division of Clinical Pharmacology, and an MS candidate in the lab, Harun Gao, who has been working on the model directly. Thank you very much.